Game recently, and I watched a spiral throw, a typical pass where, the ball did this parabolic trajectory, and the ball started out aligned, and then I realized that, of course, it's rotating around this way, but its rotation axis is constantly changing to follow the path as it goes. And I realized that I'm not 100% sure how that works. So I thought I would see just sort of the minimal physics I'd have to put in to try to understand what's going on. And what I decided is probably happening is that as normal, a spinning top, will precess around the force axis. And so it'll precess around like this. And then if that force axis is changing, and so that's from the wind resistance, so air resistance, that's constantly changing and in the opposite direction. So it's parallel to negative v, right, of the of the um, of the ball itself. And so maybe what's happening is it's just sort of spiraling around the force axis, which is what's keeping it to look like it's right on the axis. And a good thrower is going to have the original throw angle, the body of the ball to be right, have it be traveling very close to the axis of the ball. And so that precession, that little loop-de-loop stuff, is not really noticeable. And of course, I thought, well, yeah, because like the occasional pass will just kind of look a little bit wonky, right? Just like it's flopping around a little bit as it goes. And so I thought, well, maybe I could do that. So what I wanted to figure out was what does that have to look like to do the physics, right? And so let's talk about the physics of doing just like a top. So you've got the floor here, and here's the vertical direction, and we're going to take a top. I don't know, give it some shape or something, right? And then we're going to spin it that way. Is that what I want to do? Yeah. So it's original spin, or angular momentum, if you'd like, is up in that direction. And what's going on with the top is there's some center of mass somewhere that's experiencing gravity, mg, pulling down, and that's going to provide a torque around this spot. And what is the direction of that torque? Well, it's r cross f. So this is F here. So R cross F is going to give us a torque into the page. So I'll call it torque, right? And so what that means is that this vector here is going to be nudged into the page. And so that's actually what precession is all about, right? So that torque is not going to make this thing fall over. Because think about it, if there was no L, so if momentarily we thought that, pretend you're not spinning it, so you're just resting it there, well, then it just falls down. Well, why? Well, how would you describe that angular motion? Oh, angular motion. You would actually describe that angular motion as an L into the page. And that's exactly what this torque does, is it makes a non-spinning thing fall over. But if we just get rid of all that red, and we're back to having the the thing spinning, all of a sudden it just gets nudged into the page, so it just moves it around, and that just keeps happening. And so a top view is that this thing, maybe it started over here, right? It goes, and let's say that direction there is into the page. So that means that you're sitting over here. You're this eyeball with eyelashes over here, right? So it just goes like so. It'll precess around. Now, I've got another blog post that talks about how, as Feynman says, the only possible way that could happen is if it falls just a little bit first. So truly what happens is this thing falls just a tiny little bit and then goes. So what can typically happen is this thing nutates. It precesses and it nutates, which is ugly. And so, in fact, what I've done in this modeling is try to make it so that the nutation goes away. And all I've been doing for that is figuring out, okay, well, if the very first thing it's going to do is go into the page, I actually give it a little bit of initial motion in that direction since I know what it should be. And that way I get rid of the notation. So we can set that to 0 with the appropriate um, it turns out to be phi dot is how we do that. And so let's talk about let's talk about what it takes, how long it takes for this to precess around, right? So it takes some time. Well, so in a little bit of time, just give us some new space. Let's take that L. So the L is coming. Well, just let's have the force axis be down, and let's draw L in blue or something. So here's L, and it's going to go around in a circle that I'm just going to try to draw in 3D here. I'll draw that in green or something. So it's going to go around in this circle here, right? And so in the next little bit, it's going to experience a little bit of dl, a little bit into the page, which is what we just talked about. And what's that going to be equal to? That's going to be equal to tau dt. Excellent. So let's see here. So this radius here, let's call this alpha. I don't really want to use theta right now, so let's just call that angle alpha. So this radius is going to be L sine alpha. Remember, cosine's a big fat bully. It forces sine to go to the other side of the triangle. So that's L sine theta. So what happens is if I sort of redraw this from the top view, so if I come down here and I do top view of that, what we're going to have is a circle, terrible circle, and I've just gone a little bit of dl, and I've got this radius. It's just moved a little bit here. And what I'm trying to understand is what is this angle here, this little d, I don't know, let's call that beta or something, right? D beta. Well, so d beta is going to be equal to dl over r, which is L sine alpha. Excellent. So now what's interesting is we know that that is just tau dt over L sine alpha. Cool. And what that means is that d beta dt, which is the rate that this thing goes around the circle. So that's actually going to be the precession frequency. Oh, okay, so I'm just going to pull this dt over to the other side of the equation, is going to be equal to tau over L sine alpha. So what's interesting about this is it looks like the precession angle, or the precession frequency, so the time it takes to go around the circle, is dependent upon how much torque is involved, how much angular momentum you have in the first place, and how much you're off angle from the force. So what's cool though is almost always tau is just r, and then the amount of force we're talking about, and guess what? Sine alpha. So that's how, it's r cross f. So it's really cool that the sine alphas, oh, I can use the sine alphas cancel. So what that means is, and I say this to my students all the time, every time you cancel something in a physics problem, you have to be able to say physically what that means. It means that alpha doesn't matter. So that's super cool. What that means is that the precession, the time it takes, so let's think about that, the time of precession, really the period, which of course is just 2 pi over the frequency of precession. It's just going to be L over RF. Sorry, 2 pi. 2 pi. So that's really, really cool. So it doesn't matter how far off you are, like how far you've tilted the top before you let it go. If it's experiencing the same gravity, so the F is the same, and its physical length to its center of mass, which is R, is the same, then it turns out that alpha doesn't matter. So they will all precess the same amount of time, which is actually really, really interesting. So what I figured out I needed is I need this to be much less. I don't know about much less than the flight time. Because I'm thinking that if this direction changes then it just kind of precesses and follows it. It kind of spirals around it. But if if this isn't true, right? If they're like the same amount of time, so let's say the force is doing this. Remember, the air resistance is going to be opposite of the velocity. So here this thing is traveling. Well, if it takes about this much time, the time of travel, to precess once, it's going to start doing its circle, and then it's going to be like, what? What? I'm lost. And it's really just going to start flopping around, which is what really, really bad football throws do. So as long as we sort of achieve this, what's going on here? I don't know if you can see my mouse. As long as you can achieve that, then it's actually going to spiral, and just keep following the force. And if you keep it tight enough, if alpha is small enough, it'll look like a really nice spiral. So, yes, that's actually really, really cool. So, how in the world can I do this given the fact that it's going to be rotating all over the place? And so we get to these um, ways of describing it. So, what we do is we say, okay, anytime you have an object, if you've got an x-axis, a y-axis, and a z-axis, and you want to orient it, I don't know, up over here somewhere, give it a little shadow so you know where it is. And once it's there, you want to spin it around. And so we'll call that final spin psi dot. So that's spinning around itself. That's the normal spin of the top. This angle here is theta, and this angle here is phi. So um, uh, these are the Euler angles. And I've made particular choices about what's called the line of nodes, but whatever. So if I wanted to take an object and start it lined up on the z-axis and get it over here, what they usually say you should do is first rotate about the z-axis by phi. So you just kind of you bring the x over here. And then you rotate around, and remember y, of course, is also moved over. Then you rotate around the new y and you tilt the z-axis down to where you want it to go. That's pretty cool. You tilt by how much? You tilt by theta. And then you just spin the crap out of it and you're good to go. But it turns out that you can achieve the exact same result. This is amazing. You can get the exact same result. Oops, this is x, this is z. If you first pre-spin it, just leave it standing vertical up and pre-spin. So pre-spin by psi, cool. Then come on down here by theta towards x. So do some sort of where the shadow is down to here, right? Then lean towards x by theta. Then wrap this sucker out here, however far you want it to go, to phi. So psi first, theta second, phi third, which is the opposite of how you're told to do it. When you learn this stuff, you're told to do phi first, theta second, psi last, which is fine. They're both equivalent. But if you're trying to mathematically do it and you're using an x, y, z coordinate system, oh my God, is this easier? Because this is about z that never changes. This is about y, and this is about meaning like it spins around, about z again. It's literally the same z. Same z. Whereas this one over here, first you rotate around z. You do phi first. Then you rotate around some new y prime. Some weirdo y prime that's sitting out over there somewhere. And then you rotate around this new final axis, the new final side. It's crazy. So this is Mathematica's way of doing it. That's how I'm going to do it. So why am I talking about this? Because now I have a mathematical way to describe the orientation of something in space. And if I add to that the x, y, and z of the center of mass, I've got all the variables it takes to describe this thing. So x, y, z, psi, theta, and phi are all some function of time. Well, they're all different functions of time, right? And now I can describe this thing mathematically because I just need to understand the physics of how all these things are related. Well, this is pretty easy. The center of mass just obeys gravity, and if I put in some air resistance, I can slow it down. But it turns out that I didn't even bother to apply the air resistance to the travel. Because honestly, when you look at a football throw, it basically looks like a parabola. So I don't think there's a big effect going on there. And I just wanted to see if I could get this thing to precess around it and follow the force. So this is really just going to be F equals mg, and it's going to lead to a parabola. So what I mean is that the center of mass is just going to follow a parabola. Sweet. So I just need to know the dynamics of these guys. That's going to be much, much harder. Well, what are the dynamics of those guys? So what we can do is we can figure out how to do this thing in a Lagrangian style. So in the Lagrangian style, what I'm going to do is this will all be taken care of. So the only where gravity plays a role is there, because gravity does not provide a torque on the football because the center of mass is in the dead center. There is no gravity does no torque. I better write that down. Gravity, no torque. So that's not the problem. It's air resistance that provides the torque. So we have this air resistance problem, and we need to understand how it applies. So here's my theory. I'm going to say that when the football is flying through the air, let's say it's flying just a little bit off of the axis. So let's say it's actually traveling in this direction. I purposely put an angle here. So there's a very small angle alpha between the trajectory, so the center of mass trajectory, and the football. And what I'm going to say is that the air resistance on the front, so front air, is going to be different than the back air, because we know it's very, you know, turbulent, and there's way different things happening on the front to the back. So all I'm going to say is that if I can figure out how fast it's going, I'm going to have a force right here, a force of air resistance that is parallel to minus the velocity of the thing. And I'm going to say there's some r out to there, some r to the, I don't know, contact point. And I'm going to say that there's going to be a torque equals r contact point cross F air resistance out front, and I'm not going to undo it on the backside, because I'm going to claim that the back air, because of due to turbulence, um, is less, or basically I'm going to say 0. So I'm going to put all of the torque on the front and see if I can get this to work. But still, this is nasty. And it turns out I did this in the Lagrangian formalism, because when you do a typical Lagrangian, what you actually, when you do angular Lagrangians, so what we'll have is some sort of like kinetic energy is some sort of weird, um, uh, how do I want to write this? It's basically the inertia tensor, come on, the inertia tensor dotted into the angular velocity, dotted into the angular velocity again with a 1/2 out front, right? That is effectively, I'll put it in quotes, 1/2 mv squared for angles. And we just need to figure out what omega is. I'm not going to have any potential energy. I'm going to set the potential energy equal to 0. And so the Lagrangian is, when we have an external weirdo force, what we actually need to do with angles is we're going to do the Lagrangian stuff. So d really is the kinetic energy, d the angle, just whichever angle you're doing. Let's do theta minus d dt of the kinetic energy of, sorry, the dvc of the derivative of the kinetic energy, because remember, there is no potential energy with respect to the angle dot, the time derivative of the angle. And here, all you need is the theta component of the torque. So you have to figure out what the heck theta component means. If you can figure out what the theta component of the torque is, so this is hard. And you can figure out what omega is in terms of theta, phi, and psi. I said that backwards. This is hard. Hard, hard. All the rest, turn the crank. And so what you can do is we'll have a really, really straightforward set of equations for the center of mass. Truly. I mean, we're just going to have z double dot equals minus g, and that's it, right? And then we'll have some initial V initial is going to be, let's have a little bit in the x hat direction, so maybe 10 units in the x direction, 0 units in the y direction, and 10 units in the z direction. That'll give us a nice 45 degrees launch angle, and that just leads to a parabola. So all of this, parabola. But at the time, it's going to give us this. Let me use a highlighter. Ooh, highlighter. It's going to give us this. And then that's going to be able to give us the torque. And then if we can just do these two hard things, whew, we're in business. All right. So we need to go back to this to try to understand once the object has been placed in its new home, what a tiny little theta change would do, what a tiny little phi change would do, and what a tiny little whatever the other angle is. And once we can figure that out, then we've got it worked out where we can actually say, oh, wow, we can actually write down all of these kinetic energies here. So what's going on there? Oh my gosh. So here's the thing. Let's just write down what it is we're going to try to do here. So I. So this is super easy in the body frame. Because in the body frame, it's a beautifully symmetric thing. It's some number here. I'll call it 1, 0, 0, 0, 1, 0, 0, 0, and then a number less than 1, 0.3, because that's actually the easiest axis to spin the football around, right? So in the body frame, this is the football on its end. So it looks like this. Or this is, oh, I can't draw. This is the z-axis. And I'm just saying that this is the easiest spin, which is why this is the smallest number. Now, I'm not bothering getting my units right. I just need to have everything relative and we're good to go. So it's super easy in the body frame. Well, we need to be able to have, if we know something, if you know omega in the lab frame, you need to figure out omega in the body frame. Because if you know that, then this crazy I dot omega, super, super easy. Oh my God, it's like, whoop, done, right? So this is amazingly easy. You get that done. And then once you know the kinetic energy is the same either frame that you're in. So we're good to go. So if you can figure that out, then you just need to figure out if you know the torque. Whoa, what just happened? Oh my God. What just happened? Oh, I do. Oh, there we go. If you know the torque, which remember is just R, that, what did I call it? R, call it something. Contact point, cross F, which remember this is air resistance. If you know the torque, hopefully you can write that as a little bit of torque in the theta hat direction, plus, some theta, a little bit of torque in the phi hat direction, and a little bit of torque in the psi direction. Because then we know that when you do the Euler Lagrange equation for theta, you just use that. When you do the Euler Lagrange equation for phi, you just use that. And when you do the Euler Lagrange equation for psi, you just use that one. So if we can do these things, we are good to go. So first of all, how do you know? Let's do this one. If you know an angle in the lab frame and you want to get it back over to the body frame, how do you do that? Well, you just need to be able to rotate things into the body frame. And so we already talked about that, right? First, you do a rotation around z of the psi angle, and then you do a rotation about y of the theta, and then you do a rotation about z again of phi. So those are three different matrices. You just dot them into each other. And so this is the rotation matrix. So once you have your rotation matrix, you should be good to go. If you want to undo it, if you want to go the other way around, then you just do the exact opposite. You do the rotation about z of negative phi, a rotation about y of negative theta, and a rotation around z of negative phi. So this is undo the rotation. And so sometimes you need to rotate into the lab frame, sometimes you need to rotate out of the lab frame. Those are super easy to calculate. Rotation matrices are pretty easy to grab. So we're going to use rotation matrices to be able to go back and forth between the two things. So that's pretty cool. And so, all right, well, then we need to figure out what these things are. What the heck are those things? Okay. So, well, let's say that I'm out over here somewhere, which has a shadow down around here. Let's remind you, this is phi, this is theta, and and phi is just how, sorry, psi is how much it has rotated about itself. So if phi does an extra instantaneous little bit, right? Well, you realize that what that does is it moves the entire shadow a little bit further this way. So the entire thing continues to rotate about the z-axis. So guess what? Phi hat equals z hat. Easy. Oh, that's easy. Theta. Well, what the heck is that? If I were to do a slight twist of theta, make theta be a little bit better, it's going to take my guy and it's going to go down here just a little bit. Well, that's rotating about what? Well, it's rotating about the new y-axis. So the x-axis became x prime. The y-axis rotated around to the new y prime. Well, what is that? Let's see, it's a little bit of negative x. Let's see, it must be negative sine phi x hat plus cosine phi y hat. Let's check that. So when phi is basically zero, we're going to be entirely y hat. Yeah, phi is zero, the y and the y prime are the same. And if phi is 90 degrees, you're going to be rotating all around the negative x-axis. So, boom, that's theta hat. That's cool. And it turns out we're not going to need, oh no, we do need psi hat, dang it. Dang it, we do need psi hat. Um, so psi hat, psi literally is rotating about the whole thing. Well, I know what that is because that's just going to be the rotation matrix dotted into z hat. It's just taking the y-axis and rotating it into the body axis. So this, whatever that ends up being, is psi hat. Okay. So if you've got an omega, um, now we need to think about what happens if you've got a little bit of omega. So omega has got to be how phi dot is changing in phi hat direction, plus how theta is changing in the theta hat direction, plus how psi is changing in the psi hat direction, right? So that's actually really, really interesting. So it really is going to be phi dot in the z hat direction plus theta dot times this negative sine phi x hat plus cosine phi y hat plus psi dot times whatever the heck this gives you. Big, ugly, gross thing that has cosine, has thetas in it, phi's in it. And so that's what omega is going to be. Because if any of these angles do a slight adjustment in time, that is how you're twisting. And that's what omega is all about, is how are you twisting? Oh my gosh, I think we're ready. We know how to write omega down. We know how to convert omega into the body frame. We know once we're in the body frame that this is super easy, so we can get the kinetic energy. Then we know that once you have the kinetic energy, you just do the Euler Lagrange equation. Then if you know what the torque is, you just need to dot that torque into the appropriate hat, and it's either this hat, or it's this hat, or it's this hat, and boom, you get the appropriate torque to put on the right-hand side because you're going to have a phi equation, a theta equation, and a psi equation. All right, well, let's check it out. So, oops, here we go. This is how you do it. So, does this work? Oh, it does. Can I erase it? Undo. Sweet. So here's that rotation matrix right there. Oh, is there a highlighter? Oh, here's the rotation. It's not a highlighter. Whatever. Anyways, so we have the rotation matrix here, and it's exactly what I said, and I'm doing these dots just like Mathematica has encouraged me to do. The lab omega is 5 prime times big, ugly, gross, crazy thing, and theta prime times a pretty straightforward thing, and phi dot times the z-axis, so that's great. Omega body is just you rotate the matrix into there, done. Here's my the moment of inertia tensor, which is exactly what I said. Set the mass equal to 1. I don't know what the hell I'm doing. It turns out that g of 9.8 is way too strong for the other numbers that I've chosen, so it turns out g of about 0.5 is way better. I can spin it at lots of different speeds. Aim low is how much I'm aiming above or below 45 degrees. So negative 20 actually means 20 degrees above the axis. And yeah, so we're we're off and running because what we do is we say, okay, well, here's the kinetic energy, no problem. We've got the motion of the center of mass, and we've got the thing that I said, right? I thing dot omega body, which is super, super easy, and I thing doesn't change. Got our potential energy, so that's why we get a parabola. I'm not actually using power. I've basically zeroed it out, so I'm not going to talk about it. Our torque, it took me a long time to figure out just how much torque I should put in. I'm not going to really talk about that. It's a cross product of R dotted into the z-axis. So basically, a unit vector in whatever direction the football is pointing, dotted into negative the velocity. That's exactly what I said my torque would be. And so the center of mass is very simple. I'm not using power, I'm just setting that equal to 0. So this is just gravity. This is just boring parabola stuff. And then I'm using this EL1 side. So my left-hand side of the equation is going to be this. So I'm not actually using that. Yeah, okay. My left-hand side of the equation is going to be this. And that's pretty boring. And then my right-hand side is always going to be, well, let's see, it's torque dot into theta hat, torque dotted into phi hat, and it turns out I just know that the torque cannot possibly be along the axis of psi. How do I know that? Oh, because it's in the same plane. So yeah, so there is no component of torque inside. But so basically the way I've done this, it's not going to ever slow down its spin. So then I just set it, I start it at the origin, I launch it at the launch speed that I want it to do. I aim a little bit low. Phi dot has to be something. Phi dot, if I don't set phi dot to something, this thing nutates. So I just don't want it to nutate. And so phi dot, I think I'm going to skip that for now because this video is way too long. So it turns out I need to set phi dot, its initial phi dot, to be something. And if I don't do that, it nutates, and I hate the nutation. So I actually gave it an initial little like, hey, you're going to precess, let me get your precession going, since I know exactly how fast your precession should be. So I'm going to set phi dot equal to that. And then off and running, and let's see what it looks like. So, so can I move this? Yeah. So this is what a typical, oh man, go away. How do I make this go away? There we go. So this is what it looks like. Pretty cool. Looks like a football throw. And it's following the parabola. So this thing is launched, it's spinning, it's precessing, but the angle, the line that it's precessing about is moving. So there's a spiral football throw. It worked. Pretty slick. Have you ever noticed the referees throwing the balls to each other? They sometimes throw it underhand. And when they throw it underhand, it tends not to do this. Well, that's what this is. Throw it underhand, and it just kind of flies to the other referee. The only difference is this one is spinning about 10 times as fast. So I want you to do it. Pretend you're throwing the underhand throw, and then pretend you're throwing the overhand throw, and ask yourself, which one spins faster? If you spin it fast enough, it will just go like this. And what's cool about this software that I've developed is that I could do any kinds of things. I could do a crappy kids throw, right? And it just flops around. The last thing that I wanted to say is that Mathematica is great, and it just really, truly, all the work is being done by this right here. ND-solve. ND-solve is doing all the work, right? And I want to be clear that Python and I don't know, JavaScript and C++ and Fortran have effectively all ND-solve is doing. You just give it a bunch of differential equations, you give it the initial conditions, it does an Euler, it does a fourth order Runge-Kutta, and you're off and running. But that's not the value that Mathematica brings to this, because I want to show you what the equations look like. So if I scroll way down here, this is just the theta equation. This is the theta equation. And I am so glad that I didn't have to figure this out and type it in to ND-solve. I had Mathematica do all of this for me. So the theta equation, yeah, the theta equation is pretty ugly. It's got some sine double. How the hell does it have a sine double prime in it? It just does. And it has a theta double prime. And oh my God, the double primes are mixed. Yes, it is super ugly. It is not, it doesn't have all the double primes on one side of the equation. You may notice that if I go down here far enough, there's an equal sign somewhere. Yep, right there. There's an equal sign. So I've got a left-hand side and a right-hand side. And theta double prime is not sitting by itself on the left-hand side with a bunch of other crap on the right-hand side. So Mathematica does not effing care about this. And boom, it's able to run this beautiful simulation. So there you have it. This is how I think spiral footballs work.